In this demo, we'll learn how to handle a cancelled request. It's actually pretty straightforward to do this. As we noticed, cancelling a request makes the client throw an exception, a task cancelled exception. It's this type of exception we want to catch, or rather its base type, operation cancelled exception, which makes us slightly more ready for future changes. So let's surround sending the request with a try catch statement. We don't want to catch each exception, we want to catch an operation cancelled exception. What you need to do in the exception handler then depends on your use case. You might need to clean up additional resources you no longer need. You might want to navigate to another page. You might want to show an error to the user in some cases. It really depends. Important is that we catch this exception so we know what happened. The operation was cancelled. So for the demo, we'll write this out to the console. Let's give this a try. And there we go. We now see our message instead of the exception stack trace. There's one more use case to look into. As we learned, cancellation also happens when the request times out. So let's have a look at that. In this demo, we'll learn how to deal with timeouts. As we mentioned before, HTTP client will cancel the running task when a timeout happens. Let's see how that works. We add a new method, getTrailer and handle timeout. In that method, we get a trailer and we read out the response. We also surround the call into sendAsync with a try catch. So this is the same as our getTrailer and cancel method, but without a cancellation token. Let's scroll up a bit. In the beginning of the course, we set the timeout value to 30 seconds. Let's set that to 5. Now let's make sure the getTrailer and handle timeout method is called when we run the application. There we go. Now let's comment out that previous code. Alright, let's give that a try. And there we go. We again see that the operation was cancelled, this time due to it timing out. But this does seem a bit odd, right? In my opinion, it would be nicer to have this throw a timeout exception, so we can distinguish between cancellation due to a timeout and a user-initiated cancellation. However, this is how HTTP client currently, and always has been, designed. Yet change might be coming. There's a GitHub issue on the CoreFX repository where they are discussing about this. At the moment of recording, the team is still deciding on how exactly to approach this, but chances are that from Core 3.0 onwards, this will change for the better. You can follow the status via the issue on screen. If you can't wait for that, we'll look into an alternative in the module on extending HTTP client. Let's have a look at the module summary. Cancellation is important. Manually cancelling a task helps free up threads that are no longer required. Next to that, HTTP client will cancel the request itself when a timeout is reached. To allow cancelling a task, we pass through a cancellation token when making our request. The moment we call cancel on the cancellation token source that produced the token, we signal HTTP client that it should effectively cancel the request. Once that happens, a task cancelled exception is thrown. The same exception is thrown when a request times out. To handle that, we can catch that exception, or better, the wider purpose operation cancelled exception. But that's not all there is to handling faults and errors. There's a module coming up on dealing with that. But first, it's time to look into HTTP client instance management. In the beginning of the course, I mentioned that HTTP client instantiation shouldn't be surrounded with a using statement, as you don't want to immediately dispose of it. In this module, we'll learn why, and we'll learn about the new HTTP client factory to work around this problem. We'll start by covering why there's a problem with disposing HTTP client instances. Then we'll introduce HTTP client factory, a factory used to manage instances of HTTP client and the underlying handlers. we'll extensively cover different ways of using this new factory. Directly, by using named instances, and by using typed instances. Let's dive in. In the beginning of the course, I mentioned that an HTTP client instance is intended to be reused across requests. Yet, it implements iDisposable, so from that I would conclude that I need to wrap it in a using statement and don't keep it hanging around after a request has been handled. In fact, if you look at Microsoft's documentation for the using statement, it states that, as a rule, when you use an iDisposable object, you should declare and instantiate it in a using statement. Because of that, a lot of online samples you'll find will wrap HTTP client in a using statement. Even though it's counterintuitive, this is wrong. The reason is that when HTTP client is disposed of, the underlying HTTP client handler is disposed of as well. As we learned in the beginning, it's this handler that's responsible for making the actual requests. By disposing of it, the underlying connection is closed as well. So, when you re-instantiate HTTP client for the next request, a new HTTP client handler is instantiated as well, and the connection has to be reopened again, and so on. Not only is this slower, it can also lead to not having enough sockets available for opening new connections, as it does take a bit of time to completely close the connection and free up the socket. Let's have a look at what the effects are in a demo. In this demo, we'll investigate the issue with disposing HTTP client instances. We're looking at the HTTP client factory instance management service, which we'll use for this module, just as we used separate services for the other modules. Let's add a new method, test_dispose_HTTP client. Let's add the necessary using statements. And there we go. Now let's run through it. In this method, we're executing 10 requests to google.com. But rather than reusing the HTTP client instance, as we did in the previous demos, we wrap it in a using statement, so it's disposed of. The rest of the method is pretty straightforward. We use our best practice approach concerning cancellation tokens and streams, but we don't deserialize because we don't need the result. In the next module, we'll dive into handling faults and errors, so we're skipping on the try-catch statement from the previous module, for now. Let's make sure we execute this method when we run the application. So in our run action, we await a call into test_dispose_HTTP client. For that, we'll need a cancellation token source, so we can pass through the cancellation token. So we add a new cancellation token source field, and we initialize it. And then we pass through the token on that cancellation token source to test_dispose_HTTP client. Then let's ensure this service runs when we start the application. Let's open our program class. And let's comment out the line from the previous module and uncomment the line to register the HTTP client factory instance management service. Alright, let's give this a try. The requests executed correctly. So far, so good. But let's have a look at the amount of sockets that are open at this moment. For that, we open a command prompt in elevated mode, so run as an admin, and execute the netstat statement. Netstat, or Network Statistics, is a tool that's included by default in Windows, which will show us the TCP network connections, amongst other things. We add -abn as parameter. With A, we ensure all connections are listed. B ensures we see the process holding on to the connection if it's available. And N just means we want to see the addresses and port numbers in numerical form. Let's press enter. If we scroll up a bit, we see there's quite a few connections open. Most of these are from background processes like OneDrive and Dropbox. But if we scroll up a bit, we find the connections to google.com. 172.217.17.132 is google.com's IP address. We see that they are in a time-wait state. That means that nothing will be sent over those connections, but they can still receive packets from the server over them. These are the connections that we opened and closed by disposing of HTTP client. When HTTP client is disposed of, the open connection remains in this state for up to 240 seconds. And this can easily lead to socket exhaustion, which we want to avoid. Now, let's run the same test, but while reusing the HTTP client instance. Let me paste that in. We name the method test reuse HTTP client, and it should look pretty familiar. We're sending 10 requests to google.com, but we don't dispose of our HTTP client instance. Instead, we reuse it. Let's make sure we call this method when we run the application. There we go. Let's give this a try. That seems to work. Now let's execute netstat again. And there we go, one established connection to google.com as expected. It's still in established mode because our application is still up and running, so we haven't disposed of HTTP client and the underlying handler yet. This is already a lot better. Let's continue. From that demo, the solution seems obvious. Just reuse the instance by making it static, as we've been doing all along, and we're good to go. Well, not exactly. When we reuse our instance, the connection is reused until the socket is closed, for example due to a network disruption. But that means that domain name system changes aren't honored. And that's a problem, as using a DNS change to switch between different environments, like switching from staging to production, is a common scenario. If the change isn't honored, requests would still go to staging instead of production. Moreover, a lot of Azure Platform as a Service services internally use this. We can work around this by, you guessed it, disposing our instance and thus the underlying handler, but that's what we don't want to do. There's another workaround for this, which involves using a service point instance, but since .NET Core 2.1, a better approach exists. Using HTTP Client Factory for instance management. Let's check that out. To solve the two problems we just looked into, HTTP Client Factory was introduced with .NET Core 2.1. It's this factory that's used to create and manage instances of HTTP client and the underlying handlers. We'll look into how to use it right after this, but first let's learn how it solves these two issues. Whenever we use the factory to ask for a client, it will create a new HTTP client instance, but instead of recreating the HTTP client handler, which is the primary message handler, it takes one from a pool. In case of an HTTP client handler, it's that one that's used to effectively call the API. So our factory pools HTTP message handler instances and manages their lifetime. A handler is held for 2 minutes by default. So any request for a new HTTP client can share a previously created handler and thus the connection as well. Important here, as long as the handler is still in use, for example for a long-running request, it remains available. Thanks to this, our issue with too many open connections and sockets is mitigated. The handlers and thus connections are reused for about 2 minutes. The next issue was responding to DNS changes. And it's the fact that HTTP client handler instances are only around for about 2 minutes, unless they're in use, that mitigates this issue. Once a new instance of the handler is used, DNS changes are taken into account. The best practice today is thus to use the HTTP Client Factory, because next to solving those issues, it also provides a central location for naming and configuring logical HTTP clients. That's a very typical use case when you need to integrate with different APIs from your client. In those cases, you can have multiple HTTP clients pre-configured for integrating with those different APIs or microservices. When talking about configuration, that also means that we can configure delegating handlers and implement policies through something like Polly. More on that later. Let's learn how to use this in a demo.